Our universe is a strange and wonderful place. The vast cosmic dance of stars and galaxies, the intricate workings of life on Earth, and the very laws of physics that govern it all. Beneath reality lies a realm of greater mystery. This is the realm of quantum foam, a seething ocean of energy. Proposed by physicist John Wheeler in 1955, Wheeler is known for coining the term black hole. His work on quantum foam delves into space-time itself. Quantum foam is a consequence of the Heisenberg uncertainty principle. This principle states that certain pairs of physical properties cannot both be known with perfect accuracy. The more precisely we know one, the less we can know about the other. This inherent uncertainty has profound implications for the nature of empty space. Instead of being a passive backdrop, empty space is a bubbling sea of virtual particles. These particles borrow energy for their fleeting lives before disappearing back into the quantum void. To truly grasp the bizarre nature of quantum foam, we need to journey down to the smallest conceivable scale, the Planck scale. Named after physicist Max Planck, the Planck scale represents the limits beyond which our current understanding of physics breaks down. The Planck length, a mind-boggling 1.6 times 10 to the minus 35th meters, is the smallest unit of distance that has any meaning in our current theories. At this scale, space-time itself is no longer smooth and continuous as we experience it in our everyday lives. Instead, it becomes granular, like a digital photograph zoomed in to the point where the individual pixels become visible. Imagine the very fabric of reality woven from threads of energy, constantly fluctuating and vibrating. That's the essence of quantum foam. But why does this happen? Why is the universe so restless at its most fundamental level? The answer, as with so much in quantum mechanics, lies in the probabilistic nature of the quantum world. In the quantum realm, things aren't simply here or there but exist in a superposition of states, a kind of fuzzy in-between. This fuzziness, combined with the energy inherent in all quantum systems, leads to the constant creation and annihilation of virtual particles. Imagine the surface of a calm ocean. To our eyes it might seem still and unchanging, but if we look closer, we'd see tiny waves rippling across its surface. Now, imagine shrinking yourself down to the size of an atom. The ocean, once serene, would transform into a raging torrent, with waves the size of mountains crashing around you. This, in essence, is what's happening at the Planck scale. The seemingly empty vacuum of space-time is actually a churning sea of quantum fluctuations. These fluctuations, though incredibly small, are not without consequence. They can affect the properties of particles like their mass and charge ever so slightly. And because gravity, according to Einstein's theory of general relativity, is a manifestation of the curvature of space-time, these quantum fluctuations can even influence the gravitational field itself. The interplay between quantum mechanics and gravity is one of the biggest unsolved mysteries in modern physics. At the macroscopic level, where stars and planets reign supreme, general relativity provides a remarkably accurate description of gravity. But at the Planck scale, where quantum effects become dominant, general relativity breaks down. This is where the real weirdness of quantum foam comes into play. The problem is this: general relativity describes gravity as a smooth, continuous force, while quantum mechanics tells us that at the smallest scales, energy and matter are quantized, meaning they exist in discrete chunks or packets. This clash of titans has puzzled physicists for decades and is at the heart of our quest to find a unified theory of everything. Quantum foam adds another layer of complexity to this problem. The constant fluctuations in space-time, driven by the creation and annihilation of virtual particles, imply that the very geometry of the universe is in a state of perpetual flux. This is a far cry from the smooth, predictable space-time described by general relativity. One way to visualize this is to imagine a trampoline. If you place a bowling ball on the trampoline, it will create a dent, representing the curvature of space-time caused by a massive object. But now imagine that the trampoline itself is constantly being bombarded by tiny, invisible marbles, representing the quantum fluctuations of space-time. The bowling ball would still create a dent, but its position would be constantly jiggled around by the impacts of the marbles. Section 5. Borrowing from the quantum bank. How do these virtual particles even come into existence? The answer lies in one of the strangest yet most fundamental principles of quantum mechanics, the Heisenberg uncertainty principle. This principle, as we've seen, dictates that there's a fundamental limit to how precisely we can know certain pairs of physical properties. One such pair is energy and time. The uncertainty principle states that the more precisely we know the energy of a system, the less we can know about how long it will possess that energy. Conversely, if we only observe a system for a very short time, we can't be sure of its exact energy. This loophole in the fabric of reality is what allows virtual particles to exist, albeit fleetingly. They are like tiny loans taken out from the universe's energy bank. The amount of energy borrowed is inversely proportional to the lifetime of the loan. So a virtual particle with a very short lifetime can borrow a large amount of energy, while one with a longer lifetime can only borrow a small amount. These loans are constantly being taken out and repaid, with the total energy of the universe remaining balanced on average. It's a cosmic game of accounting, played out at the very edge of reality. Section 6. Black holes and quantum foam. Perhaps the most intriguing aspect of quantum foam is its potential connection to some of the most extreme objects in the universe, black holes. These cosmic monsters, formed from the collapse of massive stars, are regions of space-time where gravity is so strong that nothing, not even light, can escape. At the center of every black hole lies a singularity, a point of infinite density and zero volume. It's here, at this point of ultimate breakdown for our current laws of physics, that quantum foam is thought to play a crucial role. Some theories suggest that quantum foam might prevent the formation of true singularities, smoothing out the infinite density predicted by general relativity. Others propose that the enormous energy densities present near a black hole's event horizon, the point of no return, could amplify the effects of quantum foam, making them potentially observable. Black holes are natural laboratories for testing our most fundamental theories about the universe. By studying them, we hope to gain a deeper understanding not only of gravity, but also of the very nature of space and time. Section 7. Faster than light? The strange and counterintuitive world of quantum foam has also sparked speculation about the possibility of faster-than-light travel. Could the very fabric of space-time itself be manipulated, allowing us to bypass the cosmic speed limit imposed by Einstein's theory of relativity? One hypothetical concept that has emerged from these speculations is the idea of wormholes. Imagine folding a piece of paper in half and then poking a hole through both layers. This hole would represent a shortcut, a tunnel connecting two distant points on the paper. In a similar way, a wormhole is theorized to be a shortcut through space-time, connecting two different points in the universe. Some physicists have suggested that quantum foam, with its constant fluctuations in the fabric of space-time, might provide a mechanism for creating or stabilizing such wormholes. Imagine blowing a bubble in the quantum foam, creating a temporary distortion that could act as a tunnel. Of course, this is all highly speculative, and there's currently no evidence to suggest that wormholes exist, let alone that we could create or control them. But the very possibility, however remote, is enough to ignite the imagination and fuel our quest to unravel the mysteries of the universe. Section 8. Catching a quantum wave. Detecting quantum foam directly is a challenge of immense proportions. The effects of these quantum fluctuations are so incredibly small that they're usually drowned out by the noise of other physical processes. It's like trying to hear a whisper in the middle of a hurricane. However, physicists are an ingenious bunch, and they've devised several clever experiments to try and catch quantum foam in action. One approach involves looking for subtle variations in the speed of light. According to some theories, the foamy nature of space-time should cause slight fluctuations in the speed of light over very long distances. Another approach involves studying the behavior of light from distant quasars, extremely bright objects powered by supermassive black holes. As this light travels billions of years to reach us, it passes through vast stretches of space-time, potentially interacting with the quantum foam along the way. By analyzing this light, we might be able to detect subtle signatures of these interactions. So far, no experiment has definitively detected quantum foam, but the search continues, driven by the insatiable human thirst for knowledge and the desire to understand the fundamental nature of our universe. Section 9. Rethinking Reality. The concept of quantum foam has profound implications for our understanding of reality. It suggests the universe is far stranger and more complex than we imagine. Space-time might be a seething ocean of quantum fluctuations, not a smooth backdrop. Just as pixels create continuous images, quantum foam might give rise to smooth spacetime. This raises profound questions about the nature of reality and our place within it. Is our universe one bubble in a vast multiverse? These questions are at the forefront of modern physics. The quest to understand quantum foam is a journey into the unknown. It is a journey driven by the desire to explore and unlock the secrets of the universe.